Today we'll finish our discussion of solving triangles by talking about the law of cosines. Recall, in a right triangle, we could use right triangle trigonometry to solve it, given two sides or given an angle in a side. If we had a non-right triangle called an oblique triangle, in a lot of cases we could use the law of sines. If we had angle-angle side data given, or angle-side angle, or side-side angle, we could solve with the law of sines quickly. Finally, with the law of cosines, it will complement the law of sines. It's for oblique triangles when you're given side, 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 or side, angle, side data. So this allows you to solve all oblique triangles where there's enough information given to actually solve it. Here's how it works, given the same labeling convention that angle alpha is opposite side A, angle beta is opposite side B, and angle gamma is opposite side C. C squared equals A squared plus B squared minus 2AB cosine gamma. You don't have to label the longest side with C like I've done here. On right triangles, it's convention to put C on the hypotenuse. It doesn't matter here. You can label it any old way. That being the case, you can rotate these letters around, right? Put C up here, B over here, and A over here, and rotate their angles too. Then you get A squared equals B squared plus C squared minus 2BC cosine alpha. It's the same law, just with the lettering changed. Or, rotate it again, B squared equals A squared plus C squared minus 2AC cosine B, theta. I like this one the best. It looks like the Pythagorean theorem, doesn't it? This is a generalization of the Pythagorean theorem. That's what it is. In the special case that gamma is 90 degrees, cosine is 0, and you get the Pythagorean theorem. So this generalizes it. For a right triangle, C squared equals A squared plus B squared. But for an oblique triangle, C squared equals A squared plus B squared minus 2AB cosine gamma. Okay, so this helps to quickly solve any triangle given side, angle, side, or side, side, side information. Let's try it. Here's the first example. Suppose I'm given side, side, side data. This is kind of a fun example because you see the 3, 4, 5 right triangle, right? 3, 4, and 5. This is not a right triangle. It's 3, 4, 6. I wonder what its angle measures are, right? Well, let's try it. Given these three sides, I'm going to use the following hint. If you're given three sides, find the angle opposite the longest side first. You don't have to. You can still make this work. But if you find this angle first, since the largest angle goes opposite the largest side, these two angles will not be the largest angles. It follows that they're not obtuse, right? Not greater than 90 degrees. The triangle can have at most one angle bigger than 90 degrees. Given that these aren't obtuse, when we do the law of sines at the second step, we won't have an ambiguity. Is it arc sine or 180 minus the arc sine that we had last time? It'll always just be the arc sine, the angle between 0 and 90 degrees. So find the angle opposite the longest side first, given side, side, side data, and then you won't have to have an ambiguity at the second step. Here's the law of cosines. When we're given side, side, side data, we start with that. C squared equals A squared plus B squared minus 2AB cosine gamma. I like it too because it's ABCs, right? C squared is ABC. Think of angle C. Some books put it that way, capital C instead of letter gamma. So we put these sides in. 6 squared equals 3 squared plus 4 squared minus 2 times 3 times 4 times cosine gamma. Now you subtract the 3 squared and 4 squared over here. This is 24. Now you divide by the minus 24 and you get cosine gamma 6 squared minus 3 squared minus 4 squared over minus 24. And now, if cosine gamma is down, what's gamma? Oh, maybe gamma is the arc cosine. This is one angle whose cosine is this number. Is there an ambiguous case? Not with the law of cosines. The law of cosines is nice. Remember, the arc cosine finds you the unique angle between 0 and 180 degrees that has this cosine. That's exactly what you want in a triangle, right? The unique angle between 0 and 180 degrees. So there is no ambiguous case with the law of cosines like there was with the law of sines. It's just always the arc cosine. In this case, that comes out to be 117 degrees. This is kind of interesting too. Look, arc cosine of a negative number, is that okay? Sure it is. That just means the angle is going to be bigger than 90 degrees. Remember, a cosine of an angle between 90 and 180 is negative, so it's all right to have a negative here. and we get 117 degrees in an obtuse angle. Now, because I found the largest angle first, there's no ambiguity in finding the last side. You can use the law of cosines again, there's nothing wrong with that, it's just longer. The object of these things is to be quick as well as get the answer. You got less chance of making a mistake if you do it quick too, right? So we'll use the law of sines not because we have to, but because it's faster. Sine of the angle we just found, 117.28 degrees, is to 6. C, sine gamma is to C, as sine beta is to B. So now we know by multiplying by 4 that sine beta is 4 sine 117.28 over 6. And if beta is this, we remember from last time that beta could be the arc sine, or it could be 180 minus the arc sine. But we know it's not 180 minus, that would be an obtuse angle. Gamma is the only possibility to be an obtuse angle. In fact, it is an obtuse angle, since it's opposite the longer side. Beta can't be, it must be the arc sine only. The ambiguity is gone. The arc sine of this number, 4 sine 117.28 over 6, is 36.34 degrees. I said up here, round to 2 decimal places. So you start at the decimal point and go to 2 digits and round here. So whatever this was, made it round to 0.34. Finally, do the easy thing on the last step. Don't do lots of work and maybe make a mistake by doing too many calculations, right? Just take 180 minus the other 2 angles that you found, and you get 26.38 degrees. So on the side, law of cosines, followed by the law of sines, followed by the sum of angles theorem, gets you the answer the fastest. Let's try another one. Here's a case that comes up once in a while. We just found the angles for a 3, 4, 6 triangle. Let's find the angles for a 3, 4, 8 triangle, right? 3 by 4 by 8. Don't waste your time. No such triangle exists. Remember the sanity check we did last time? One of the 3 things in a sanity check was to make sure that the sum of these 2 sides is not bigger than this side. Well, 3 plus 4 is 7 is 8. That can't be. The shortest distance between 2 points is a line. This is not the shortest distance. It's not a line. 7, how can that be less than this? It's an impossible triangle. You simply immediately say, no such triangle exists. So check that when you use the law of sines for a side case. If the sum of these 2 is greater than 8, then a triangle exists, and you solve it like in the last example. Alright, so that's the side case. What about the side angle side case? Here's an example. And a lot of these are applied problems. That's really fun. One of the great things about trigonometry, I think people like better than algebra, is there's lots of immediate applications. An aircraft heads due north at 300 miles per hour for 3 hours. I used to do these kind of problems. I worked for the FAA as a subcontractor. For 3 hours, while another heads at a bearing of 120 degrees at 320 miles per hour at the same time. How far apart are they after 3 hours? This is like that terrible train problem, right? That you always see in algebra, except there's different directions now. The trains head opposite directions, but here the aircraft had different angle of 120 degrees from each other. Here's the first hint. On these applied problems, always draw a picture, right? Often that gives you an idea what's going on much better. So I draw the first aircraft going up this way, just put a little airplane here. The second aircraft going up here with 120 degrees between them, it says. This one heads at 300 miles per hour, this one at 320 miles per hour. I want to know how far apart they are, so I label what I want to find, C. I label the angle I'm given, and I label the 2 sides I know. If I go for 3 hours at 300 miles per hour, MPH stands for miles per hour, can also be written as miles divided by hours. If you write it that way, miles divided by hours times hours, the hours cancel and you get miles. So 3 times 300 is 900 miles on this side. That's how far that plane traveled. On this side, 3 hours times 320 miles per hour, the hours cancel. 960 miles this plane has traveled at an angle of 120 degrees. Now you see the triangle and look at what we have. Side, followed by angle, followed by side in that order. Side, angle, side. So we go to the law of cosines. We have to find C. Well, again, we write down my favorite law, the generalization of the Pythagorean theorem. C squared equals A squared plus B squared minus 2AB cosine gamma. And that's 900 squared plus 960 squared minus 2 times 900 times 960 times cosine 120. Some of these problems, they give you a special angle, like airplanes often take off at particularly special angles. If it's 120 degrees, we already know that from the special triangle. We don't have to run that on the calculator. You can put it in the unit circle and draw a little triangle. Or maybe you can just kind of figure it in your head by this point. Cosine of 120 degrees is minus a half. So we'll just figure that the 2's cancel and the minus cancels. You've got 900 squared plus 960 squared minus 900 times 960. All this other stuff canceling. If you take that square root, you've got 1,611 miles. When you're done, I recommend that you do the check. Is this one bigger than this one plus this one? 900 plus 960, yes it is. Is it reasonable to think it's about 1,600? I mean, if it was 200, you'd say, well, I don't know, well, that's 900, that's, you know, just do the sanity check, see if it seems like it's right. This one, we can't do all the checks because the object wasn't to solve the triangle, it was only to find this one side. So you just see if it looks reasonable by that easy, quick check. Here's another one. Another side angle side problem. Suppose I want to solve this triangle with side C equals 12, side B equals 10, side alpha equals 70. I like drawing these triangles, but the fact is, this one I can recognize immediately as side angle side without even drawing it. If I have the two sides B, C, and the angle for the other side, this is the one that goes between these two, right? Angle alpha goes between B and C, angle beta between C and A, and angle gamma between A and B, right? So it's these two letters and the angle that goes with the other side, then it's always side angle side. And so you start to recognize this after a while. But draw it, and then you can be careful. And now I'm going to write in the other order. Here's the hint on side angle side. When you're given side angle side, use the law of cosines form that has the angle you're given in it. If I'm given alpha equals 70 degrees, I'll use the law of cosines form that has alpha in it. So I'll put a squared equals b squared plus c squared minus 2bc cosine alpha, this form of the law of cosines this time. Well, let's see, I put in 70 degrees. The reason for that is so I use the 70 degrees. The other two forms, I can't use the 70, and so the law of cosines does me no good. Just like the law of sines, I want to get all but one number known in the equation, and then I can solve for it. All right, so a squared equals 10 squared plus 12 squared minus 2 times 10 times 12 times cosine 70 degrees. I square root that, and I see that a is the square root of all that. And if you run that on your calculator, you find out that comes about 12.7. Now, it's just like before. You start with the law of cosines because it's a side angle side case. But in the next step, the law of sines is easiest, right? And then the last step, we'll do that in a second, let's say. On this second step, here's the hint again. You don't want to get that ambiguous case of the law of sines. So how can we avoid it in the side angle side case? We find the smaller angle by the law of sines of the two that remain. I have alpha. Which one is the smaller side? Well, there's an angle gamma opposite C and angle beta opposite B. Remember, the smaller angle goes opposite the smaller side, so I should find beta. It will be the smaller of the two angles. If it's not the largest angle in a triangle, then it's acute. It has to be the arc sine, not 180 minus the arc sine. So what I'll do is use the law of cosines. Then I'll find the angle corresponding to the smaller side, beta, B. So I say sine beta is to 10, B, as sine alpha, 70 degrees, is its opposite side, 12.7, by the law of sines from last time. Now we have to solve this. So we multiply by 10, and then we take the arc sine. And there's no ambiguity, because beta must be acute, not being the largest angle in the triangle. Arc sine of 10 sine 70 degrees over 12.7 is 48 degrees. We now finally, in the last step, do the easiest thing. Sum of the angles is 180 degrees, so gamma must be 180 minus the two angles we found, must be 62 degrees.